Now let's start with the definition of current, and current is the rate at which electric charges move through a given area. And again, right away notice it says rate. It says rate. So when you hear rate, you know it's per given time period. So right away we know that this is going to be some sort of a amount of quantity moving in a given time period. So it's electric flow. Think about flow rate of water, like a river. A river has a current as well. This is the electric current. So some examples are machinery, appliances, computers, or like, the veins in the human body. These are obvious ones. This not as much. There's also electric current that's going through the central nervous system of the body. So current in general, but specifically electric flow we're going to talk about. Now the formula here is I equals delta Q over delta T, where delta Q is the change in charge, okay, the electric charges that move through a given area over a given time period. So it's a rate given time period. So how many coulombs pass per second over a given cross-sectional area? And the units of current are ampere, abbreviated with capital A, and named after Andre Marie Ampere. Another thing to notice is that this I here in the front comes about because current was originally in French phrased intensité de courant, or in English current intensity, and the phrase is just simplified to be current, but it's current intensity, and the intensity gives the I there in the front. So first remember that with conductors we're really looking at the flow of electrons, but it's also possible for protons to flow. Now what we're going to think about is that a flow of positive charges, well, that really gives the same electric current and has the same effect in the circuit as an equal flow of negative charges in the opposite direction. So it doesn't really matter which way to think about it. Traditionally we say that the direction of current is opposite the movement of negative charges, and this is just completely arbitrarily defined. So to summarize, remember that in metals, or most things that are made up of wires and other conductors and electric circuits, the positive charges are really immobile, they're not moving. So the charge carries again are the electrons, but because the electrons carry negative charge, the motion of the electrons in a metal conductor is really direct, is the opposite of that of a conventional current. And finally, we could also think of a combination of positive and negative flow, and this can exist. And this happens when you have gases and dissolved salts. So when we're looking at things that have ions in them, so they make the fluid into an electrolyte, and then you can have positive and negative flow through those fluids. But again, we're looking at metals and circuits and conductors. So example 1 says the startup current for a standard refrigerator is around 15 amps, but the running current is around 3 amps. For a 10-second time interval, how much more charge passes a given point in the circuit during the startup mode than in the running mode? So again, here we're now going to look at the value of Q in each of these situations, or delta Q in a sense. So I want to find out what the difference in Q is in this problem. Well, I can think to myself here, I've got a value of I for the starting point, and I've got a value of I for the running current. So I could start by writing the fact that I know my formula is I equals the change in Q over the given time period. So since we're looking for Q here, we're going to have I times delta T equals delta Q. Now since we're looking for the charge in two different situations, if we do this twice, we could say to ourselves, alright, well we have I1 times 10 seconds, because the time interval isn't changing, and that's going to equal delta Q1, the change in charge in the first situation, and then we have I2, the running mode of 3 amps, again times 10 seconds, that's going to equal delta Q2. In reality, we're looking for the difference in these two, so we're going to have, again, 15 amps times 10 seconds, or 150 coulombs. How do I know it's coulombs? Because an amp is really a coulomb per second. Here I'm going to have 3 amps times 10 seconds, and that equals delta Q2, so this is a value of 30 coulombs of charge. So what's the difference, or how much more is running? 150 and 30, so 120 coulombs of charge every 10 seconds compared to its starting mode to its running mode. And now this makes sense logically, because think about a refrigerator. When you start it up, the refrigerator is right out of the box. The air inside of it is room temperature. It has to cool down, it has to remove all the heat. So it's going to run at a high current initially, and then once it gets going, once it's cooled down, it's going to maintain that state of equilibrium running at 3 amps and drawing less current. Let's talk about drift velocity now, and drift velocity is the net velocity of a charge carrier moving in an electric field. So this is in the circuit. So let's really take a look and think about the fact that current has to do with the number of coulombs of charge that pass a given point in a circuit in a given period of time. And because of its definition, it's also a lot confused with the idea of drift speed, but drift speed or drift velocity really refers to the distance traveled by the charge carriers per unit time. And like the speed of anything, we're looking at the distance to time ratio. So here, the typical path of an electron through a wire could be described as chaotic. It zigzags back and forth with collisions with the metal atoms, and each collision results in a change in the direction. So because of all these changes, it's like every time it goes 5 feet forward, it comes back a little bit, like another 2 feet, or 3 steps forward, 2 back, the idea. Now, when there's a battery connected to this, the electrons continue to migrate and move forward, but they move very slowly. And the overall effect of them is these high-speed collisions that the drift speed is really, really low. It's typically as low as like a meter every hour. A meter every hour. Think about how slow that value is. In meters per second, some are such as low values of like 2.5 times 10 to the negative 4 meters per second. So we're talking really, really low velocities. Now, you can say to yourself, well, how does this make sense? Like, how can the current be so high if the velocity is so low? Well, the idea again is that current is not really velocity, but it's the rate at which the charge carriers cross on a given point in a circuit. For example, if I had a really, really wide pipe and a lot of water were passing there, it would have a very high volumetric flow rate. That's what this is. It's a volumetric flow rate. In this case, we're looking at the amount of charge carriers or electrons that cross a given cross-section. So if I have a cross-section that's, a really small cross-section, only a few electrons might be able to pass through here or whatever it is, right? But if I have a much larger cross-section, then there are many of these that can carry through here or that can cross in a given time period. So they don't have to be moving fast as long as there are many, many of them moving across a given area in a given time period. That's what current really is. It's not really the speed, but it's how many move across a given area in a time period. And again, this cross-section of the wire here indicates or shows how this works differently. The current here is much higher than this current, for sure. To give another analogy, suppose there was like a really large race with a ton of really, really slow turtles running. And say the race was only like a meter in length. And there were like 10,000 turtles on the starting line. And after 30 minutes, a lot of the turtles reached the starting line. Well, this would have a really, really, really low drift velocity because, again, they're not really traveling with a high velocity, but the current would be very large because the turtles are like the charge carriers. There's a lot of turtles in that short time period that are passing that given point. So in this analogy, again, we're talking about how many turtles cross the finish line at the same time or in that certain amount of time that we're looking at. Now, the next real question is, well, why isn't there a delay when you turn a switch on, but it immediately turns on, right? Wouldn't there be a noticeable quick delay there? And the answer is no, there's not. And the explanation has to do about what's called a charge carrier, as we've been saying. So charge carriers in wires, they're electrons. And the electrons, they're just supplied by the atoms of copper or whatever the material is made of in the wire. And once the switch is turned on, the circuit's then closed. And what this really means is that there's a battery that's connected or a potential difference, a high potential and a low potential, a positive end and a negative end. That's why we talk about the potential difference. And the circuit signals this electric field and it travels at the speed of light and it tells all the electrons in the circuit to start moving. So they all start moving at this low drift velocity. But they all start moving at the same time. It's like a bunch of soldiers in line and they hear the order, like forward march, and they all start marching at the exact same time. So as soon as the electric field, which itself travels at nearly the speed of light, tells them all to do that, they all start moving instantly. Well, remember, it's not like electrons are like really moving throughout there. The electrons are already in the copper wire, in the filament, in the light bulb. So inside the light bulb, the charge carriers, they're already there. They just have to start moving and carrying that charge, actually. So the light bulb begins to light, and the charge carriers begin to move, but at a very slow rate, but they feel it instantly because the electric field tells them that almost instantly. Another analogy is to think about like your pipes in your house. When you turn the faucet on, the water immediately comes out of the spigot. It doesn't like wait, there's no delay or anything like that, because you have to think about the fact that the pipes, they're already filled with water. And as soon as you turn the pressure on, then all the water starts to move together. Well, these circuits, they're already filled with electrons, and the electrons just begin to move through the wire. They move from atom to atom, the electrons just keep carrying. So they keep moving, and when the electrons that were in the filament originally all end up leaving, because they eventually will leave that filament, other ones take its place from the wiring that was existing there. So the electrons are just moving from piece to piece. So we're going to look at two sources of current that generate current, and the first example are batteries, and batteries convert chemical energy into electrical energy. So you're looking at a battery that has an anode and a cathode, and that anode and cathode create a potential difference, and the current is carried throughout there. The second is a generator, and a generator converts mechanical energy to electrical energy itself. And examples of this are like hand cranks, a dam, a steam engine, or a combustion engine, a wind turbine, a lot of different examples there. Now, a generator is not to be confused with a motor. A motor takes electrical energy, converts it into mechanical. So here we're looking at a generator, and a generator has some mechanical input. And the example here is a simple generator inside of a magnet creating that current that powers that light bulb at the end there and the electrical output. So now let's take a look at the difference between direct and alternating current. A direct current is when a charge moves only in one direction in the circuit, where like for example, battery whose terminals are fixed. Other examples of things like solar cells or thermocouples, they're fixed. So the direction of the circuit only continues in one direction. And what we'll notice is that the current is a constant, right? We're seeing the current value does not change. That's what direct means, or fixed. It's also good to know that direct current used to be called galvanic current. Now, AC current, or alternating current, is the motion of the charges that they continuously change between forward and reverse. And the idea is like a generator whose terminals are changing. So think about a positive and negative end of a battery. The electrons are going to want to flow toward the positive end, right? But then imagine if that end kept switching. The electrons are going to go back, then forth, then back, then forth, then back, then forth. The idea of alternating. Electrons are going back and forth like this. So there's really no net motion of the charge carriers. They're kind of like staying still, but they're just going like this, back and forth, and vibrating at really high frequencies. Now, if the vibrations, if they were slow enough, somebody would actually notice this. For example, in like flickering of lights or other appliances. The frequency in the US of alternating current is 60 hertz. And this is a good frequency because we don't really see that flickering.